Yeah, thank you. Hello everyone, my name is Jiayue. I'm a second-year master's student from Roman and ISRQI research group. And today I'll talk about a project with my undergraduate supervisor, Andrew Frey. It is a subfield of quantum information in gravity called holographic complexity. And this is based on our recent paper, complexity scaling and phase transition here. And this is our outline. First, I will provide you with some background information, like the concept of complexity and also the AdS5 correspondence. And then I will talk about the holographic complexity proposals. And I will give you an introduction to the magnetized AdS soliton. And then we will evaluate the holographic complexity for 3 different proposals. And finally, I will make a conclusion. First, let's begin with complexity. You might ask this question, what is complexity? It is similar to ask how hard it is to do a task or how many steps you need to solve a problem. And in quantum circuit model, quantum complexity is defined as a minimum number of quantum gates that you need to reach a target state from our reference state. Here, psi is our target state. Here, psi is our target state, and psi naught is our reference state. And the minimum number of quantum gates, the minimum number of G's here, are the complexity. And what is AdS5 correspondence? AdS is the anti-de Sitter spacetime. It is a spacetime that has lective cosmological constant. And in Poincare coordinates, this is a metric for the anti-de Sitter spacetime. And here, r is a radial direction, x is a spatial direction, and t is a time direction. And when r approaches infinity, it is our boundary of the AdS. And the conformal field theory is just a particular quantum field theory that is invariant under conformal transformation. And what is AdS5 correspondence? The AdS5 correspondence was first proposed by Marcena in 1997. The basic idea of the AdS5 correspondence is that there is a gravitational theory in d+1 dimension and living in the bulk, and there is a conformal field theory in d dimension living on the boundary, and there is a duality, or say there is a correspondence between the two theories. And the quantities that can be computed in the one theory that can also be computed in the dual theory. Like a famous example of this AdS5 correspondence is the holographic entanglement entropy, saying that the entanglement entropy of a subsystem living on the boundary is dual to the area of some extremal surface in the bulk. And by here, I want to say that the entanglement entropy is not enough. This idea was first proposed by Seskin in 2014. He considers two-sided AdS black holes, and at the time equal 0, the two horizons of the two horizons meet together at time equal 0, and the volume of this wormhole, or the volume of the black hole interior, is 0. And as time goes by, as we can see, the volume of the wormhole or the volume of the black hole interior grows. And it will grow linearly with time, and the growth rate is exactly proportional to this area, or the area of the event horizon. And but we can also know that the black hole entropy becomes a constant at a very quickly, and the entropy is saturated. So we need something else to capture the growing geometry of the wormhole. So Seskin proposed that the thing that we need is complexity. So this is our motivation for the holographic complexity. This is the argument that the volume of the black hole interior grows linearly with time, and also the complexity of states also grow linearly with time. So we have the complexity is proportional to some volume, and here G Newton L is just something that we added to make this formula dimensionless on the right-hand side. And the concrete statement is that the complexity of the boundary safety state is proportional to the volume of the maximal volume slice. And here are some steps to help us evaluate the complexity using the complexity equals volume conjecture. First, we need to choose a time slice sigma on the boundary. And next, we consider all the space-like hypersurfaces B that's anchored on this boundary sigma. And then we vary these hypersurfaces to find the one that has a maximal volume. So we can use this maximal value to compute the holographic complexity using this formula. But as we can see in this formula, L is some arbitrary length scale, so it is a little bit ambiguous. And why can we use this arbitrary length scale here? So to avoid this ambiguity, another proposal was proposed. It is complexity equals action conjecture. It is saying that the complexity of the boundary safety state is proportional to the action of the Wheeler-DeWitt patch. And the Wheeler-DeWitt patch is just the union of all the space-like hypersurfaces that we considered before. So the boundary of this Wheeler-DeWitt patch is just the non-boundaries. So this whole region is our Wheeler-DeWitt patch. And the conjecture says that the complexity should be proportional to the action of this region. And here, the dimension of action is h bar, so we can make this thing dimensionless without introducing an arbitrary length scale L. And here are some steps to help us to evaluate the complexity equals action conjecture. First, we need to choose the time slice sigma, and then we consider the union of all the space-like surfaces, and we compute the action of this region, so we can find the complexity. And there are another proposal called complexity equals volume version 1. It is just that we consider the space-time volume of the Wheeler-DeWitt patch. And now let's move on to the magnetized AdS soliton. In our paper, we investigate the holographic complexity of the CFTs compactified on a circle. And the periodicity of this circle is called delta phi, and there is a Wilson line around this circle. And as we can see, as R decreases, the proper size of this phi circle will get smaller and smaller, and when R approaches R0, the circle vanishes. And to avoid a conical singularity here, we need the phi has a periodicity called delta phi. And let's make a comparison between the AdS soliton metric and the periodic AdS metric. As we can see, when we let the f of r equals 1 and r0 equals 0, we can reduce it to the periodic AdS case. And the AdS soliton has a cigar-like geometry without horizon, and the AdS is a cylinder-like geometry with a horizon. And now let's evaluate the complexity using the three different proposals. For the CV conjecture, the value of the maximal volume slice is just this integral. It's very easy. And as we can see, when R0 equals 0, it is an AdS case. And but here is a problem. There is a divergence in this formula. Rm will approach infinity. So in order to cancel this divergence, we introduce the complexity of formation. It is just the complexity of the magnetized AdS soliton minus the corresponding complexity of the AdS. So our complexity is just proportional to this part. It's proportional to R0 to d minus 1. And as we know, R0 is proportional to 1 over delta phi. So we can get that the complexity is proportional to 1 over delta phi to d minus 1. And if we plot this complexity, we can get this diagram. It is a function of the Wilson line, and when we increase the Wilson line, we will find that there is a phase transition from this AdS soliton to the AdS case. And for the CV version 2 and the CA conjecture, we need to find our Wheeler-DeWitt patch. And this diagram shows the shape of our future light shades, this area. And we can also have a past light shades. So this figure helps us to define our Wheeler-DeWitt patch. And so if we have a space-time volume in this region, we can compute this integral. And if we plotted this CV version 2 versus the Wilson line, we can get that the AdS soliton also scales as 1 over delta phi to d minus 1. And there is a phase transition at this point from this AdS soliton to the AdS case. And for the CA conjecture, it is a little bit complicated, but we just need to evaluate the action of this Wheeler-DeWitt path region. It has a bulk action and also the boundary action for these non-boundaries. And there is also a joint action term for the joint is just the intersections of our known boundaries. And if we plot the CA versus the magnetic flux, or say the Wilson line, we can also observe the phase transition from the AdS soliton to the AdS. And here are just all the proposals that I put together in one slide. As we can see, they have the same scaling behavior and they have the same phase transition behavior. So in conclusion, we evaluated the holographic complexity for CFTs and compactified on a circle with a Wilson line. And for all the 3 different proposals, we find the same scaling behavior and the same phase transition behavior. So these are the common features that they all share. That's all. Thank you.